Let's finish up 5.5. It's on something called a U substitution or the substitution rule, or sometimes we'll call it a change of variables. We went through how to do that, and what we did so far is we basically went through and we did some relatively simple examples. Remember, we use a U substitution when we can see a function and its derivative in the integrand, or a constant multiple of its derivative. And we went through and we basically changed all the variables to be written in terms of U. Did a whole bunch of examples, and we left off with these two problems right here undone. So let's go ahead and pick up right there and do these problems. So again, usually we're going to choose U to be the inside of some other function. Because then when we differentiate that, that'll provide the chain or that other derivative that appears in the integrand. So on this one, our guess would be that U equals e to the x, this e to the x, because that's on the inside. And then du, so we need to change that differential of x into a differential of u. So this is going to be e to the x dx. So here's an e to the x dx, so I'll put a du in its place. And then wherever there's this e to the x, I'm going to put a u there. So here's what I've got. I've got minus, this stuff is just a du, and this is the cosine of u. Okay, so let's see. Again, when we're anti-differentiating, especially with sine and cosine and some of those trig functions that have negatives in them, you've got to think about this. So when you differentiate cosine, you put a negative in there. So when you anti-differentiate it, you don't. Does that make sense? So this is going to be negative sine of u. And if you just differentiate that and double check, you do get negative.
What about the
oh, whoops, thank you. Forgot about the 2, okay? So we'd have negative 2 sine u plus c. And then the only other thing that we need to do is change back from u's into x's. So our answer is negative 2 sine of e to the x. I'll put that in parentheses, plus c. And there's our antiderivative, okay? Any questions there? Okay, pretty simple example to start out with. Okay, let's take a look at this next one here that we left undone. This is a little bit more complicated. We could choose u to be 1 minus x squared, but then the derivative of that is only negative 2x dx. Okay, and I've got this other 1 floating around there. The negative is fine. We can deal with that. But this one's a little bit more complicated. If you let u equal 1 minus x squared, that doesn't take care of the whole thing. Okay, it comes close, but not the whole thing. So we're going to do this in just a second. But let me go ahead and erase this. Here's the hint. Separate and then do a u substitution. Okay, so the trick that we've used quite often is we've taken this and we'll write this as 2 separate pieces. So I'll write this as 1 over square root 1 minus x squared dx. And then I'll write minus x over square root 1 minus x squared dx. Does any part of that look familiar? One over square root 1 minus x squared is sine inverse. Okay, so the antiderivative of this piece is sine inverse of x. Okay, now we just wrote down a possible substitution to deal with something like this. So if we let u equal 1 minus x squared, the derivative of that would be negative 2x. So there would be an x right there that we'd need there. So we can see a function and its derivative or some constant multiple of its derivative. So let's go back to this. Let's let u equal 1 minus x squared. That means du would be negative 2x dx. So I'm going to do this. I like that negative being in there, so I'm going to put a plus right here. And I don't need the 2, so I'm going to multiply both sides by 1/2, and I'm going to get rid of that right there. Okay? So the 2 would be gone from this side. So wherever there's a negative x dx, I can put a 1/2 du. So this is going to be plus the integral of 1/2 du. And then this stuff goes on the bottom, so this is the square root of u, and I could put a 1 there. And then we could clean this up just a little bit. This would be 1 over 2 square root u du. And that should look really familiar. What's that? That's the derivative of the square root function, right? So if I antidifferentiate this, then I get the square root of u. So I've got the antiderivative of this first term right here, the antiderivative of this second term right here. So the end answer for this one is the sine inverse of x plus, well, I need to reverse the substitution here, so this would be square root of 1 minus x squared plus c. Okay. Any questions there? Make sense? Okay, now we're going to take a look at a couple that are a little bit more interesting. So let's take a look at example 6, and let's see if we can figure out what happens if we don't see a function and its derivative in the integrand. Can we somehow manipulate it so that we can make it appear that way? So could we use some properties of maybe exponentials or trig identities or different things like that, or maybe logarithms, in order to come up with some relationship between x and our change of variables u, what we're going to use to substitute. So this one right here, you could stare at this one for a while. I remember the first time I saw something like this, it took me quite a while to figure out how to do this. This is in the section that talks about substitution. So this has to be able to be done using substitution. Okay, the only two techniques that we're going to go over in this class are recognize the end result of a differentiation formula, or doing a substitution to make it look like the end result of a differentiation formula. Okay? So I'm going to give you about 10 seconds to look at that. Can we see a function and its derivative in the integrand? And the answer to that is, regardless of how you try, the way it's written right now, the answer is no. Okay? So we do a clever trick. And this is one of those that you might just want to put in your tool bag and come back to it some other time. I'm going to multiply the top by e to the x and the bottom by e to the x. So I'm multiplying by a 1. And what this is going to do is it's going to give me this. I'm going to have e to the x. I'm going to put the dx on the end. And then if I distribute that through, here's what I get. I get e to the x times e to the x. That's e to the x squared. If I wanted to write that this way, I could. If I wanted to write it this way, I could. But the most advantageous way to do this, because we're talking about undoing the chain rule where we've got an inside function and all that sort of stuff, I'm going to write this as e to the x squared. And then what's e to the negative x times e to the x?
0.
E to the 0, which is 1. Okay. Now, all we've done is just cleverly rewritten this. Can you see a function and its derivative in the integrand? And could we choose one of those functions whose derivative appears in the integrand, that inside part, could we choose that to be u? Okay. This right here is the inside, and if I let u equal e to the x, then du equals e to the x, dx, which is that stuff right here. So here's what I've got. E to the x dx is du, so I'm going to put a du on the top. And then this is e to the x squared. E to the x is the same as u, so this is going to be u squared plus 1. And again, for some reason, if they're written like this, they don't look as familiar. Okay, remember, if you've got a du or some differential in the numerator, you can just slide it on the end and then put whatever constants there. So on this one, I'm going to put 1 over u squared plus 1 du. And then this is the integrand right here. Hopefully that looks familiar. Tangent. Okay, so this is going to be tangent inverse of u plus c. And then all we need to do is just change back in terms of the variable that we're after. It was in terms of x's, so this is going to be tangent inverse e to the x plus c. If we found the derivative of this, take a good look at this. We know how to differentiate tangent inverse. it would be 1 over whatever we're taking the tangent inverse of squared plus 1, and then times the derivative of whatever we were taking the tangent inverse of, which is e to the x, so the derivative there is e to the x. And then you can see right there. Okay, so we've got the right answer on that one. Any questions? Okay,
So
yeah. What?
that's just going to take some time.
Time to look at it.
Yeah.
This is the trick right here. Okay, and again, I would really recommend you can most of the time you can get the answer. If you're not convinced or you're still thinking, my gosh, that's weird, I'm not quite sure how this works, go ahead and find the derivative of your antiderivative, and you'll be able to see how we've got that inside function. We found the derivative, left that inside function alone, and then we've got that chain rule sitting there, that other derivative of the inside function floating around there. Okay. All right, so let's take a look at this one here. Hopefully you took a look at your notes over the long weekend. We actually showed something similar to this before, but we're going to find the antiderivative of tangent. Antiderivative of tangent. And if you look at it right now, is there a function and its derivative in the integrand? What would it be? Well, you could say x is the inside function, and then its derivative or its differential is dx. So then we could say u equals x and du equals dx, and let's take a look at where that gets us. Literally just change the variables, that's all. Okay. So certainly that isn't going to get us anywhere because that just goes in circles. We've got the same problem we had to begin with. Could we rewrite this somehow? Okay, so let's rewrite this as the sine of x over the cosine of x dx. And then let's think about this. There are a couple different ways we could try and do this, but only one way that this is actually going to work out. So we want to think, we've got to find a function whose derivative also appears in the integrand. So u equals, okay, our guess is cosine x, and that's really the best guess based on the practice that we did last week. Usually if we let the denominator have something to do with u, if we let that be the inside function, usually that's going to work out better. Because when I find the derivative of this, I get du equals, even though I introduce a negative, right? Wherever there's a sine x dx, here's a sine x dx, I can just move that to the other side, and I get a negative du. It's all up in the numerator where I need it to be. If I were to make the choice of u equals the sine of x, then du would equal cosine x dx, okay? It's not down in the denominator where I need it to be, okay? So not the right approach there. So let's go ahead and change the variables here. Wherever there's a sine x dx, I'm going to put a minus du, so that's a minus du. And again, if you wanted to, let's go ahead and put that 1 there, and let's put the du on the end. That may make it a little bit easier for us to recognize the derivative. And then wherever there's a cosine x, we're going to put a u. So that's what I've got. And I can certainly slide that negative out front also. And then it looks really familiar. What's the antiderivative? ln. So I'm going to have a negative ln absolute value of u plus c. And then I just need to reverse the substitution, so I end up with this, negative ln absolute value of cosine x plus c. Okay. Here's the problem, though. If you look at this in a textbook or find this in an integral table, that's probably not what you're going to see. What you're going to see is this, the ln of secant of x plus c. That's usually what you'd see. What did they do from here to here? Okay, move the negative up here, move that power, this product, this factor out here, used it up there using the power property for logarithms. Then cosine of x raised to the negative 1, that means reciprocal, and the reciprocal of cosine is secant. Okay, so that's usually how you're going to see it. Okay, although I think it might be a little bit easier to evaluate with the cosine there, just because we understand those and are a little bit more comfortable with those. Okay, any questions? Okay, let's do some more interesting stuff. Let's take a look at this one. Now I'm just going to show you how to do it because this will take forever. Okay. This is really a pretty cool technique. So here's what we're going to do with this one. Just like we do usually, sometimes we're gonna choose that denominator to be the u. And notice we've got a couple advantages here. It's the entire denominator and it's got two terms right now, but when I differentiate it, it's only got one term. So I get du equals dx. So if I were to replace what I've got so far, I can put a u right here. I can put a du right here. But then I've still got an x right there. So everything is good here except for I've got this integrand in terms of two different variables right now. Does anybody see something that I could do? Maddie? Very good. Okay, every one of these is an equation. When we set up this equation that relates u and x, it's an equation that we can differentiate, we can manipulate using all the rules of algebra that we're used to. Okay? So if I take this and I say, you know what, x is the same as u minus 2, then I can replace that x with a u minus 2, and here's the advantage now. When I had two terms in the denominator, I can't break that into two different smaller pieces. I can't break it into its parts. I can do that right here, and what I end up with is u over u minus 2 over u du. So I've got 1 minus 2 over u du. And I can find the antiderivative of each one of those pieces. What's the antiderivative of 1 with respect to u? Just a u. And what's the antiderivative here? Negative 2. If you had to write it, do this. Put the 2 out front and put the 1 there. That's the derivative of ln. So this is going to be the ln absolute u plus c. And then we just reverse the substitution. Okay? Very clever trick. This is what I would call an advanced substitution technique. Okay? So wherever there's a u, I just need to reverse this. So this is going to be x plus 2 minus 2 ln absolute x plus 2 plus c. Any questions? Okay. Okay, this one's done using the same technique. Okay, but this one's a little bit more complicated, so let's take a look at this. This has to be able to be done using a substitution technique. So what would we guess u is? The u squared plus 1, right? So we're going to say u equals, x squared plus 1. So we'll differentiate that. So we get du equals 2x dx. Okay, let's start replacing and see how close we come here. So this is going to be, well, that's just a square root u. Let's see, I've got a 2x and a dx. I don't need the 2, so I'm going to move the 2 to the other side by multiplying by a half. Everybody okay with that? Actually, let me keep this here, and I'll write what I've got here. 1/2 du equals x dx. Everybody all right with that? So what I've got right now is I've got x squared times x dx in the numerator. So wherever there's an x dx, I can put a 1/2 du. So I can replace the two of those with a 1/2 and a du. What have I not replaced yet? The x squared. So let's take a look at that for just a second. There we go. We're going to take this and we're going to rewrite this as x squared. If you see an x squared, you can put a u minus 1 in its place. So wherever there's an x squared right here, I'm going to put the u minus 1. Okay, now let's see what we've got. Again, I've got two terms here. So I'm going to write this as the integral. I'm going to put the u over 2 square root u. And then I'm going to write minus 1 over 2 square root u du. What can I do right here? Yeah, this has an exponent of 1, this has an exponent of 1/2. I can cancel this half with that 1. So I end up with a u to the 1/2 on the top, right? So I end up with u to the 1/2 over 2 on that one. Okay, which I can find an antiderivative for pretty simply, right? Just anti-power rule, increase the exponent by 1, divide by the new exponent. Do I need to rewrite this one?
Nope.
Nope, that one looks pretty good, doesn't it?
Yep.
So the antiderivative here, increase the exponent by 1, so that's going to be u to the 3/2. Divide by the new exponent, or that's a fraction, so we'll flip it over. So that's going to be 2/3. Let this catch up there. And that's that 2. And then this is minus, what's the antiderivative of 1 over 2 square root u? Square root of u plus a c. And then we'll just clean this up a little bit. So I'm going to cancel the 2 with the 2. So this is going to be 1/3 square root u cubed minus square root u plus c. Okay, and it's just algebra here, right? We're going to reverse the substitution, so wherever there is a u, I'm going to put an x squared plus 1. So this is going to be 1/3 square root of x squared plus 1 cubed, and then minus square root x squared plus 1, and then plus c. Any questions? Yeah.
Why did you write u to the 1/2 over 2? I don't get that step to the next step.
This one right here?
That, yeah.
Right
From,
here.
From there to
From-
the next step.
Oh, to this? Okay, let me blow this back up. To go from here to here?
No, from there.
From here to here.
Yeah.
Okay, increase the exponent by 1, so that's going to be 3/2. And then instead of dividing by 3/2, we multiply by 2/3,
All right.
so the 2's would cancel. Okay? Yep, increase the exponent by 1, divide by the new exponent. That's the anti-power rule. Okay? All right. Okay, now we're going to take a look at some problems that make it, we're not just finding antiderivatives, we're actually going to be calculating definite integrals, but we're going to do it using the substitution technique. So, let's ignore this for the time being. Ignore the fact that this is a definite integral. Let's just look at this as a substitution problem. What would we choose for u? Sine of x? Because we'd normally write this, I'm going to cross this out from here, we'd normally write that. This is the idea. It's the sine of x raised to the 4th power. So we're going to use the substitution technique, okay? But remember when we were talking about definite integrals and we were introducing this notation, when you think of this, everything in here has a variable attached to it. This is a function of x, that's a differential of x, and these need to be limits of x. Everything in here has to be written in terms of the exact same variable. So if we're going to do the substitution technique and we're going to change from x's to u's, we better be really careful about the way we do that and make sure that everything gets changed or changed and then changed back. Okay, so I'm going to show you 2 different techniques for doing this problem. Okay, the first technique is change everything so that it's written in terms of the new variable u. Okay, which is the one that I like and I think most people like and I think most of the time works out the best. Or if you really like doing this way, I'll run into maybe 20% of the people that they like doing the substitution technique, but then they like to change back to the original variable. I'm going to show you both, and I'm going to show you why I like changing everything in terms of this new variable. Okay, so let me show you that first technique. So here's what we do. We're going to say u equals the sine of x. That makes du equal to the cosine of x dx. So I've got my replacement right there. So if I were to do this, okay, don't write all of this down. This is going to be u to the 4th, okay, because remember this is sine of x raised to the 4th. That's my u. There's cosine x dx, so I'm going to put a du there. I can't, so don't write this down, I can't just leave them this, I can't leave them this way, okay? Because these are limits of x. So what I'm going to do is I'm going to go ahead and change those. I'm going to find their u equivalent, we'll call it. So I'm going to come over here and I'm going to take this and I'm going to evaluate this at the lower limit, negative pi over 2, and at the upper limit at pi over 2. And I'm going to write down what u equals. So if I plug in negative pi over 2, what is the sign of negative pi over 2? Negative 1, okay? And if I plug in a pi halves, what is the sign of pi halves? That's going to be 1, okay? So the new lower limit in terms of u would be negative 1, and the new upper limit in terms of u is positive 1. Make sense? So what I've done here, if I look at what I had up above, what I've done here is I've changed everything that used to be in terms of x's, I've now written it in terms of u. So the cool part about this is I never have to change back to x's. I've written their u equivalents here, and I can just go through and do this problem. So this is going to be u to the 5th over 5, evaluated from negative 1 to 1. So this is going to be 1 raised to the 5th over 5 minus negative 1 raised to the 5th over 5. Well, that's 1/5. I've got 6 negatives all together here, so that's going to be a positive. And I end up with 2/5. Okay? And that's the answer. I am not quite sure what this looks like, but this is an even function, and that's an even function. So whatever it looks like, if I add up the area from negative pi halves to pi halves, I end up with 2/5. That's my net area. I've got more positive area than I do negative area, and since this is raised to the 4th, it's got to be all positive. Does that make sense? Okay. We're also going to look at this again in a couple of minutes just because of the nature of that function, because of the symmetry. But let me show you how to do it if you were going to change the variables, find the antiderivative, and then reverse the substitution. So we're going to do the same steps to start off with. We're going to say u is equal to the sine of x, du is equal to the cosine of x dx. I think of it as an indefinite integral, so I'm going to write that as u to the 4th du. The antiderivative is u to the 5th over 5. Do I need the c on there? Not because it's going to be a definite integral. And now I change this back. I'm going to change this back to sine of x to the 5th over 5. And now I go ahead and I evaluate it from negative pi halves to pi halves. So this is going to be the sine of pi halves raised to the 5th over 5 minus the sine of negative pi halves to the 5th over 5. Sine of pi halves, 1 raised to the 5th, so that's going to be 1 over 5. Sine of negative pi halves, let me make sure that looks like a negative. That's going to be negative 1 raised to the 5th, that's going to be minus 1/5. So in either case, I end up with the answer 2/5. Okay. I like this much better. I like changing everything in terms of that variable u. If you're stuck on, it was x's to begin with, I like finding that antiderivative, and then I slap those limits of x on here once I've changed it back so that it is a function of x. If you want to do it that way, it's fine. Okay? But I think 9 times out of 10, this works out to be a much easier definite integral to compute. Okay? We're doing a bunch of things here. We're evaluating a trig function and then taking that answer and raising it to the 5th. Whereas here, we've evaluated it kind of separately, kind of compartmentalized, figured out what the answers are, slapped those on here, and then we never have to think of the sine function or the x's again. Okay? All right. So let's run through and do a couple more practice problems then using this technique. So again, you'll notice that each one of these is a definite integral. we're going to use the substitution technique, and I'm biased. I like changing all the variables, so I'm going to say u is equal to 1 minus r squared. We do that for a couple reasons. It's got two terms, one of which is a constant. That'll go away when we differentiate, and it's the inside function. So that means du is equal to negative 2r dr. I don't need the negative and I don't need the 2. So I'm going to rewrite this as negative 1/2 du equals r dr. And I'm going to change all the variables. So I'm going to evaluate this at the lower limit of 0 and at the upper limit of 1. So this will tell me what my new limits of u are. If I plug in a 0, I get a 1. And if I plug in a 1, I get a 0. I'm plugging in the lower limits and upper limit of r. Good there? So I've got to change the limits, I've got to change the integrand, and I've got to change the differential. So this is going to be from 1 to 0. Lower limits 1, upper limits 0. That's how they correspond. Then I've got, in place of an r and a dr, I'm going to put a negative 1/2 du. And in place of the 1 minus r squared, I'm going to put a u. Now I can rewrite this as 1 to 0, negative 1/2 u to the 1/2. I can do it that way. Or does somebody see something else that I could do to make this a little bit easier? What's that? Negative, let's see.
Or u, root u over 2.
Radical, we could write that as a radical.
Yeah.
Okay. If it were in the denominator, it would make more sense. I'd probably want to leave this as a power function here. I'm looking at this negative sign right here, and I'm looking at the lower limit being a 1, and we're integrating backwards in the negative direction to 0. What could I do?
We could just flip it.
Okay.
And take the negative out.
I could change the order of integration. I could integrate from 0 to 1. I could integrate in the positive direction. Remember, if I change the direction of integration, I throw another negative in there, which makes this positive 1/2 u to the 1/2 du. Sure. Yep. Yeah, you'd get the same answer. It's just most people make fewer mistakes with less negatives. Okay, so if we get rid of the negative, then we're in better shape. Again, let's see. Ben, what am I going to do to integrate this one?
Add 1 to the half.
Increase the exponent by 1. That's going to give us 3/2. So this is going to be u to the 3/2. Multiply by 2/3, and we already had a 1/2 there. So I get u to the 3/2 over 3, and I need to evaluate that from 0 to 1. Which I'm going to think of the square root of u cubed over 3 evaluated from 0 to 1. Is that okay? Again, not calculus, just rewriting. U to the 3/2 would be the square root of u cubed. You can put the cube inside or you can put it outside. It doesn't matter. Usually it's nice to keep it outside. That keeps the root a little bit smaller. So if I plug in a 1, what do I get? I get a 1/3. And if I plug in a 0, I get 0. So the answer on this problem is 1/3. Any questions? Okay, let's take a look at the next one then. Think about what you'd use for u. And hopefully on this one you can see why it would be so much easier to change all of the variables to begin with. What's our choice for u? Secant? What's the derivative of secant? Secant tangent. What's the derivative of tangent? Secant squared. Okay. If you rewrote it, you could do either one. Okay. Which one's probably easier? Probably tangent. So if we let u equal the tangent of theta, then du equals secant squared theta d theta. There's our substitution for our differential right there. And the cool part about this is let's go ahead and change the limits of integration. Let's evaluate this at 0 and at pi fourths. So we go from something that I think most of you are less comfortable with, trigonometry, to take a look at this. What if I plug a 0 into tangent? What is the tangent of 0? And what's the tangent of pi fourths? 1. So if I change everything, my new lower limit is 0, my new upper limit is 1, and this is just u, and this is just du. Could it get much simpler than that? U squared over 2, evaluated from 0 to 1, 1/2, 0, answers 1/2. Again, you think of the trig functions, you kind of deal with those all together, change variables into u's, and then you never have to go back to that. Any questions there? Okay, I'm not going to finish this one, but we will set it up. What's our choice for u? T squared, that would be the right choice. Because du equals 2t dt. There's a t, there's a dt. I need that to be a 6. Again, my personal preference here is to change this so that it looks right. I'm going to multiply this side by 3 and that side by 3. And I'm going to change the variables here. So I'm going to plug in a 1 and a 3. That's going to make my new lower limit and my new upper limit. So this is going to be a 1 and this is going to be a 9. So this is going to be the integral from 1 to 9. Wherever there's a 6t dt, I'm going to put a 3 du. And wherever there's a t squared, I'm going to put a u. So what's the antiderivative? 3e to the u, and we're going to evaluate from 1 to 9. We'll just finish it off because this one's pretty easy, right? Any questions? Okay.
What would you write 3 to the numbers?
Yeah. Okay. Let's see if we can buzz through these and finish these up before class is over. If I need to keep you after for a couple minutes just to finish, I think it'd be worth it. What would you be here? Not bad, right? Looks horrible right here, but take a good look now. If you go ahead and evaluate our substitution, our change of variables, if we put an e in and then an e to the fourth, ln of e? 1. ln of e to the fourth? 4. So this is going to be the definite integral from 1 to 4. Okay, there's the dx on the top and the x in the denominator, so that takes care of these guys right here. So this is just going to be a du, and this is 1 over square root of u. Anybody know what the antiderivative is without looking? It is 2 square roots of u. One way that you could do that would be if I need a 2 down here so I can recognize that, let's multiply by 2 and let's divide by 2 at the same time. So this antiderivative would be the square root of u with the 2 sitting out front. If you need to, so this would be 2 square root of u evaluated from 1 to 4. If you need to, don't write that. Rewrite this as u to the negative 1/2. Again, increase the exponent by 1. Divide by the new exponent. The new exponent is 1/2. Instead of dividing by 1/2, we times by 2. Same answer there. And then you can finish that off, right? Okay, let's take a look at this one. What would we choose for u? Inside function, again, two terms, one of them is a constant. So if I choose this to be 3t minus 1, then du is 3 dt. I just need a dt, I don't need this, so I'm going to do 1/3 du is the same as dt, and I'm going to change everything here. So I'm going to plug in a 0 and I'm going to plug in a 1. So that makes my new upper and lower limits of u. This is going to be, well, let's see, I plug in a 0, I get -1, right? Plug in a 1, I get 2. So we're integrating from -1 to 2, and this is just 1/3. We're putting 1/3 du in place of that, and in place of 3t minus 1, we're putting a u, so that's u to the 50th. So this would be u to the 51 over 153, right? Evaluated from -1 to 2, okay? Not a ton of fun either way, but my gosh, think about trying to do that by multiplying that out. Wouldn't be very fun, okay? Any questions? Whoops. Okay, so I'm going to show you a couple more things to finish up, one of which you're going to see quite a bit of in 1220, so just as kind of a precursor to that. You'll find answers to these in an integral table, but the way we do these is we use a power reducing formula. So if you try really hard on this one to do this using substitution without rewriting it using an identity, it's not possible. So the identity that we use is a form of the double angle identities. It's called a power reducing formula. If you see sine squared of x, you can write 1 minus cosine of 2x over 2. So let's go ahead and do that. Let's rewrite this one using that power reducing identity here. So this is going to be the integral of 1 minus cosine of 2x over 2 dx. And let's see why this would be an advantage. I could at first break this up. I could do 1 over 2 minus cosine of 2x over 2 dx. Can I find an antiderivative for this piece of the integrand? Just be 1/2 x, right? Okay. Now, if I were going to anti-differentiate this, technically here's what I'd do. So I'm going to rewrite this as two completely separate pieces. I'm going to do 1/2 dx. And then I'm going to write minus, I'll have the 1/2 out here, cosine 2x dx. So this one is just a 1/2 x. If I were going to do this one, I mean, you might be able to think your way to what the answer would be. Remember, when you differentiate cosine kx, you end up with another factor of k out front. You multiply by the factor of k. So if we're anti-differentiating, we're going to be dividing by a factor of k. But let's see how that works. If I say u equals 2x, then du equals 2 dx. But I don't need the 2, do I? So I have a 1/2 du is the same as dx. So I've got minus 1/2 integral. Wherever there's a dx, I'm going to put a 1/2 and a du. And then this is cosine u. So what I've got here is -1/4 integral of cosine u du. And what's the antiderivative for cosine? Okay, just plain old sine, right? So this is going to be 1/2 x from this term right here, and then this is going to be 1/4 sine x plus c. So if I find the derivative of 1/2 x, I get 1/2. If I find the, not the x, what mistake did I make? Yeah, this would be a u, but we need to replace that with a 2x. There we go. Okay? So we anti-differentiate this. We get a sign of 2x. Instead of multiplying by the 2, we end up dividing by another 2. That's why there's a 1/4 sitting out front. Okay? Any questions there? Okay. The only difference between the two of these, notice in the power reducing formula, it's going to be 1 plus cosine of 2x over 2 dx. So what's the only difference in the answer going to be? It's going to be a plus rather than a minus. Okay? So this antiderivative would be 1/2 x plus 1/4 sine 2x plus c. Any questions? Okay, last little bit, and some people think these aren't worth understanding or knowing, but these can really come in handy, especially when the author of a textbook wants to make their point. If you think about this problem right here, which we've done before, okay, we actually looked at this before we even knew how to evaluate using the fundamental theorem of calculus. The sine function from negative pi to positive pi looks like this. And we know that because of the symmetry, this right here would be negative and this right here would be positive. So the answer on this one is 0. The definite integral, the net signed area, ends up being 0. So this was an odd function on an interval symmetric about the origin. So because it's an odd function, whatever we accumulate on this side is going to be canceled out by whatever we accumulate on this side. Okay, because it's an odd function. Remember, whatever value we get going to the right, we get the exact opposite value when we go to the left. Okay, that's why it's above here and below there. Okay? If it happens to be an even function like the cosine function, cosine from negative pi halves to pi halves, okay? We've got just kind of one loop here, one lobe of this function. So we'd want to add this up. Well, one thing that we could do here to potentially make it easy, because sometimes evaluating with 0 is better, because this is symmetric about the origin and it's an even function, we know that this left side and the right side would be exactly the same. So what I can do is, instead of integrating over that entire interval, let's just integrate half of it. Let's go from 0 to pi half. Let's deal with the positive part of it, the right side of it. And then what adjustment would I make to the answer? Just times it by 2. Okay? And that's an easy antiderivative find. You're going to find that this ends up being 2. The answer to that is 2, because when you antidifferentiate that and evaluate it, that integral is going to have a value of 1, and then we double it. Okay? So we can summarize these in this little box right here. It says if we've got a function that's continuous on a closed interval from negative a to positive a. So in other words, it's symmetric about the origin. We go the same amount to the left as we do to the right. If it's an even function on that interval, then we can just integrate on the right side from 0 to a, and we can double the answer. Maybe that's an advantage sometimes, just being able to evaluate it at 0. Maybe that makes it a little bit simpler. If it's an odd function, then the answer is always 0. But again, these rules for symmetry, this box right here, depends on it being symmetric about the origin. Okay, so that interval's got to be symmetric about the origin. Okay, there are some other rules for symmetry that could apply, but let's take a look at this right here. Okay, this is symmetric about the origin. So if we knew that this was an odd or an even function, we might be able to make it easy. Okay, what is it? Happens to be odd. Remember, the test for odd and even start out the same way. You plug in negative x, and you simplify. On the numerator, we get x squared. We get negative x cubed, and I get plus x. And then it's usually a good idea to write the negative, pull that negative out front. So the top is x squared, and if I factor out a negative, it's going to be x cubed minus x. So compare this answer to the original function. It's the exact opposite. So that means it's odd. So why is reviewing some pre-calculus, some stuff that you learned in 1050, a good thing to do here? Because the answer is 0. You don't have to do any integration, no substitution or anything like that. Got it. Okay? Any questions? Okay. And what about this one right here?
It's even.
That is an even function. So the advantage that you'd have here is you could just double the answer from 0 to 3, x to the 2000th dx. So this is going to be x to the 2001st over 2001, evaluated from 0 to 3. And then again, we double that answer. But again, the advantage you have here is one of these is really easy to evaluate. When you plug in a 0, you get a 0. So the answer on this one is 2 times 3 to the 2001st over 2001. And that's it. Because when you plug in a 0, you just get 0, right? Okay, any questions? Okay, that finishes up 5.5. We've got one more section to cover, and then that's it.
Oh
Okay.
my gosh.